Assalamualaikum, and a very good day to the organizers of 8th International Conference on Advanced in Computer Science and Information Technology, and fellow presenter, and also to fellow audience. So I am Nasuha. You can call me Nasuha. So today I will present my research titled Scalable Link Prediction in Twitter using self-configured framework. So I'm from University of Malaya, Malaysia. All right, so my research focuses in the domain of link prediction. So this link prediction focuses in social networks platform. So we use social network platforms such as Facebook, Twitter, and also Instagram to connect to our friends, to share our daily stories, and to get latest news that happening in the world. And then this link prediction is very significant for suggesting friendships, infer behaviors of social network users, and also predicting criminal activities. So to describe this link prediction in social networks, I've divided in a taxonomies and divided into 4 categories, which is the first one is measures. So link prediction can be used in terms of 2 measures, content-based or graph-based. And then for approaches, link prediction has 4 different categories of approaches. Previously or initially, researchers use similarity, and then they are moving to using a probabilistic model, and then algorithm like machine learning and metric factorization. And then now the trend is moving to it using hybrid, where they combine 2 of this approach, whether they combine algorithm and similarity, or they combine probabilistic and similarity. And for applications for link prediction, the big category for link prediction can be detection or recommendation or influence analysis. And this is a social network context that previous researchers have considered to analyze or conducting this link prediction analysis in these social networks. So they have conducted directed network, weighted network, bipartite network, cross, dynamic, heterogeneous, and sign networks. So traditional link prediction approaches perform efficiently in single computing environment. Even so, the approaches are not well suited for most of the large-scale networks in terms of its performance and efficiency. So meaning that when we use smaller social networks, we have good performance when we use the traditional link prediction method. But when we when we use the traditional method inside of the large-scale social networks, we found out that they are less perform and less efficient. So like here, Zhu et al. In 2019 has proposed a scalable link prediction in a distributed computing, meaning more than one computer. So in a distributed computing environment for good prediction performance of large-scale networks. And then they have proved the improvement on the prediction execution time for 1 GB of data in 220 seconds. Okay, so this is the review of some literature for my research. So for the first table, it highlights the trend of link prediction approach. As I mentioned just now, the link prediction approach is moving toward using hybrid, where they combine the similarity and probability. And this one is combined similarity and algorithm. So all of these related works are focusing are proposing to use a scalable link prediction to cater the large-scale problem for link prediction in social networks. So this is the network that they use. Most of it is social networks. All right, and then for the second table, it highlights the most used model for Scalable. So the most used is for researchers. We obviously focuses on open source. So here they are using MapReduce in Hadoop, and then these 3 PCLP, SPLPA, and this DTLPLP are using Prager model in GraphX. And then except for this one, DDPM, they developed their own combination of scalable model between fork join and vertex-centric Pregel. So, however, they have their work have limitation. For example, for CBRA, their limitation is the map reduce involve heavy input and output. So it's not suitable for graph processing. Link prediction is mostly using graph iteration during the process. So map reduce have a heavy input output. So it will affect the system performance, or the time will delay the overhead. We have overhead. So, and then for PCLP, their limitation is that they are using this GraphX, and then this GraphX involves lots of message generation and transfer. So this also will affect the overhead communication time. And then for the last one, the TLPLP, they are using hybrid, and then Pregel model in GraphX. However, their limitation is the algorithm or the link prediction approach that they use is network dependent, meaning that the algorithm was better at dynamic interaction rather than social relations. So the problem statement for my research work is that, as I explained, several works has proposed scalable link prediction for huge networks. And then, however, the processing in scalable and distributed nodes is less performing and have overhead communication time that affect the execution time performance and resource inefficiency. So meaning that in distributed computing like this, so it has overhead communication time and resource inefficiency. And in addition, we have to manually configure the big cluster with high computing specifications in order to perform best in large scale social networks. So when we want to configure with high computing specifications, it means that we have to use many CPU cores, and we have to have thousands of nodes in order to have to perform well for larger scale networks. So my research significance is that almost 3.8 billion people were active internet users as of April 2020, stated by Statista. And then for this research also for continuity focuses on link prediction analysis in massive social network. And then also majority of an existing successful solution is implemented in single computing. So we are moving to a distributed computing. And then the last one to contribute to finding a novel way on how to make link prediction compatible with large scale data. So the method for this research is that first we conduct the literature review, and then we collect the data and experiments to answer the question of what is the effect on scalability of different data and workload during the prevailing link prediction execution. And then we did a framework design and development to answer the question of how is formulation of self-configured framework to perform link prediction with scalability for large-scale social networks. And then lastly, we evaluate the framework to answer the question of how has the proposed framework improved when compared with existing solution in terms of their performance and efficiency. All right, so this is the proposed self-configured framework. This is the full architecture of the self-configured framework, which we adapt autonomic computing inside of this, and we integrate in Apache Spark cluster. This is the open source, and I believe most of you have heard this one. And then we adapt autonomic computing concept. And then previously we have to manually configure, meaning that when we want to execute application inside Apache Spark, we have to manually configure how many cores or how many memories that we want to use. But this self-configure proposed to collect and then predict and decide the best configuration for submitted application automatically 1 second before the Spark application submits to worker nodes. So this is the worker nodes. So this framework receive input of the Spark submit command, and then the application jar. The application is the link prediction application, where there is detection or clustering or influence analysis or recommendation, and then the data. And then for the output of this framework is that the self-configured application properties. So this framework resides in the master of the cluster. So this is the worker, this is the master. So this framework only resides on the master node. And all of these reconfigurations occurs before Spark submits the application execution. And then the inside of the self-configured framework, we develop or we design the 3 kind of modules that adapt the autonomic computer concept. Is that that is the first one is collect, and then decision making, and then this update. This is the autonomic computer concept, and it will automatically performing and decide what's best for the submitted application. Okay, so this is the 3 module. So the first one is collect. So this collect module will read application and environment properties right after user submitted the Spark submit command. And so this is the input lah, Spark submit command, and then the application Java file and also the data. And then the output is the user's configuration, user's cluster specification such as memory and CPU, and then the application workload and data size. And then the second module, the decision making. The aim for this module is to analyze the application and the environment properties with trained XGBoost model and predict the best configuration, then plan the new configuration. So this is the input, the master memory, master core, worker node, worker memory node, worker core node, data size, application complexity, and memory capacity. So this is the process, and the output is a new configuration value of 10 value of this. So the driver core, memory overhead, memory instances, and then for executor memory, executor core, and default parallelism. And last module is update module. So this module will condition Spark to use the new plan configuration for the specific execution. So the input is the new configuration value decided by decision making, and then this module will output a new configuration successfully updated and submitted to master node to proceed with application execution in the worker node. All right, so we mentioned just now we use XGBoost in decision making module. So we use this classifier model to identify the best executor per node for certain case. This certain case is such as big cluster, small cluster, higher core, low memory, big data size, or complex workload to provide the best configuration before application execution. So in XGBoost classifier, we generate all type of case studies and form 16 million rows of different case. So the generation of this all kind of case studies include 1, 2, 3, 4, 8 features. So we have core ranging from 4 to 32 core, and we have memory features ranging from 4 GB to 1 to 8 GB. And then we have worker node 1 to 8, and then this is increasing level of application complexity, and then this is increasing level of data capacity inside of our cluster, and then the last one is the data size. So the different case study aims to cover all possible kinds of users applications submitted to Spark framework for execution. So that's why we cover from smaller to biggest case. So in this XGBoost use boosting techniques to make sure we get the best result at the end, and then XGBoost also can increase the speed and performance. So that's why we pick XGBoost to suit our self-configured framework inside of Apache Spark cluster. We don't want to use something that need more time, because the execution of large-scale social networks analysis is consuming more time, so we don't want to add more time. So XGBoost increase speed and performance of the classifier. And then we implement this XGBoost in Python as an API that return EPN value decision making model. So so this is the process of the decision making. So we collect all of this data, and then this is inside of the XGBoost, and then we will update the best application configuration. All right, so for configured properties in update module, so there are over 20 types of properties that we can control in Spark framework. And then this research, however, focuses on only 8 application properties based on shipment 2016. They have conducted an analysis, and this 8 is the most related to what affecting the system performance, such as time and resources, So this is the 8 configuration properties that we handle. So the first one is Spark driver core. So we also set, this is the default value set by Apache Spark. This is our rules of thumb that we set. So for driver core, we only include 1 to 8 driver core, and for the driver memory, only 1 GB to 4 GB. Then, for example, for executor core, we only we do not want it to be more than 5, because if it more than 5, it will affect the overhead of the processing. And for parallelism, we set to be more than 2. All right. Okay, so this is the case study that we include in our evaluation of this self-configure framework. So we set up 2 different Spark cluster. The first one is in Azure Ubuntu 16.04 server to set up bigger cluster, and the second one is in CentOS 17 for smaller cluster. So there's 3 types of cluster that we set, which is the 2-node cluster, 4-node, and 8-node cluster. So all of this represent how many worker node that we set in the cluster. And then memory configurations in our case study, we range up from 2 GB up to 32 GB. And then this is the data that we use, is 73,000 of node and 24 million of edges. But however, we divided these 24 million edges into a variety of sizes. For example, from 100,000 of edges until 1 million of edges, so that we want to access the scalability of our framework. And then the applications that we use to submit to the Apache Spark is that these 3. So the first one is that graph clustering, and then the second one, overlapping community detection, and the last one, redundant graph detection. So all of these applications, we develop it to be scalable link prediction. And then, however, it uses 2 different models. For example, the first 2 is using Prager model in GraphX, and the last one is using MapReduce model in Hadoop. Okay, so for the results of our case study evaluation, so this is the time performance on SCF on self-configure framework. So this is all of the experiment specifications, or we call it case studies. So all of these case studies, these 2 is the one that EM2G and EM6G is the one that we're not using the self-configure framework, and the other 10 is the one that using self-configure framework. So focusing on this application or OCD applications, this graph clearly indicates improvement in time taken for the SLP execution. So for example, this okay, so it's almost 40% lower than EM2G and EM6G. If you see here, almost 40% lower in terms of their time performance when they are using self-configure framework. So this is for the success rate. So we have 3 applications. So this graph highlights that we want to highlight these RGD applications. They are now able to increase their success rate of execution. Previously, when we are not using self-configure framework, RGD is not able to pass 50% of success rate. So now they are able to up until 100%. Because this RGD is using MapReduce in Hadoop, so it usually cannot pass with our data. Okay, for resource utilization, so this resource utilization is the combination of the usage of CPU, memory, the network transfer rate, and also the disk utilizations. So this is the node that we use. This is the 4-node cluster. So all of these different colors represent the node, and the size of the ring is represent the case study. So we can see that the resource utilization rate of each case is at almost similar value, and it maintain the scalability and prove the balanced resource utilization in each execution. So to compare the self-configure framework with our related works, so we can see that in this first table, we highlight the cluster capacity value. So SCF is at the second lowest cluster capacity value. Cluster capacity value is how bigger is the cluster. So our research focus on low end cluster setup. So we do not want to have bigger cluster capacity because we want to save the cost, or we don't want to spend much to perform best for this analysis. So we focus on low cost cluster. So SCF has the second lowest cluster capacity after SPLBA. And then to compare the time performance, SCF also achieved the second best time performance, 216 seconds, using only as low as 16 cluster capacity. And this proves that SCF provides better performance due to its intelligent decision process based on XGBoost and self-configured setting that not only give best instance configuration, but also in a low-cost cluster setup without human intervention. And so to conclude, so our self-configured framework is integrated in automated computing and classified using XGBoost model into existing spot in generic and reusable way to any types of applications. However, our research only focus on link prediction applications, and you are welcome to use any applications with our framework. And as also we have experiments with varying case studies ranging from small to bigger cluster and also varying data size on top of 2 different computing server, Ubuntu and CentOS. And then SCF has shows 40% improvement in time performance, and then a more balanced resource utilization, which did not exhaust for small cluster computing. And SCF is capable to scale from 100,000 to 1 million each list of Twitter users by auto-tuning the configuration of 10 application properties for each submitted application, which only take a second before their execution. So in the future, we plan to add more data into our evaluation of each case studies. So this study limitation is that usability of self-configured framework limited to Apache Spark framework. So if you want to use this framework, you have to install Apache Spark first. However, this framework can further be implemented or developed inside other big data processing framework. And then this study also exclude data partitioning as a factor contribute to scalable link prediction enhancement. And the last one, this study only focus on low cost cluster. So yeah, thank you.